Indonesian Petroleum Association, and co-organized by Diandra Promosindo. Platinum sponsor Pertamina melalui Pertamina Hulu Energi sebagai subholding upstream. Gold sponsors BP Indonesia, Mubadala Petroleum, Medco Energi, Schlumberger. Silver sponsors Chevron, ExxonMobil, Inpex, Petronas, Premier Oil, A Harbor Energy Company. Bronze sponsor Repsol, supported by Indonesian Ministry of Energy and Mineral Resources and Special Task Force for Upstream Oil and Gas Business Activities. Organized by Indonesian Petroleum Association and co-organized by Diandra Promosindo. Platinum sponsor Pertamina melalui Pertamina Hulu Energi sebagai subholding upstream. Gold sponsors BP Indonesia, Mubadala Petroleum, Medco Energi, Schlumberger. Silver sponsors Chevron, ExxonMobil, Inpex, Petronas, Premier Oil, A Harbor Energy Company. Bronze sponsor Repsol, supported by Indonesian Ministry of Energy and Mineral Resources and Special Task Force for Upstream Oil and Gas Business Activities. Organized by Indonesian Petroleum Association and co-organized by Diandra Promosindo. Platinum sponsor Pertamina melalui Pertamina Hulu Energi sebagai subholding upstream. Gold sponsors BP Indonesia, Mubadala Petroleum, Medco Energi, Schlumberger. Silver sponsors Chevron, ExxonMobil, Inpex, Petronas, Premier Oil, a harbor energy company. Bronze sponsor, Repsol. Supported by Indonesian Ministry of Energy and Mineral Resources and Special Task Force for Upstream Oil and Gas Business Activities. Organized by Indonesian Petroleum Association and co-organized by Diandra Promosindo. Platinum sponsor, Pertamina, melalui Pertamina Hulu Energi sebagai subholding upstream. Gold sponsors, BP Indonesia, Mubadala Petroleum, Medco Energi, Schlumberger. Silver sponsors, Chevron, ExxonMobil, Inpex, Petronas, Premier Oil, a harbor energy company. Bronze sponsor, Repsol. Supported by Indonesian Ministry of Energy and Mineral Resources and Special Task Force for Upstream Oil and Gas Business Activities. Organized by Indonesian Petroleum Association and co-organized by Diandra Promosindo. Platinum sponsor, Pertamina, melalui Pertamina Hulu Energi sebagai subholding upstream. Gold sponsors, BP Indonesia, Mubadala Petroleum, Medco Energi, Schlumberger. Silver sponsors, Chevron, ExxonMobil, Inpex, Petronas, Premier Oil, a harbor energy company. Bronze sponsor, Repsol. Supported by Indonesian Ministry of Energy and Mineral Resources and Special Task Force for Upstream Oil and Gas Business Activities. Organized by Indonesian Petroleum Association and co-organized by Diandra Promosindo. Platinum sponsor, Pertamina, melalui Pertamina Hulu Energi sebagai subholding upstream. Gold sponsors, BP Indonesia, Mubadala Petroleum, Medco Energi, Schlumberger. Silver sponsors: Chevron, ExxonMobil, Inpex, Petronas, Premier Oil, Harbor Energy Company. Bronze sponsor: Repsol, supported by Indonesian Ministry of Energy and Mineral Resources and Special Task Force for Upstream Oil and Gas Business Activities. Organized by Indonesian Petroleum Association and co-organized by Diandra Promosindo. Platinum sponsor: Pertamina, melalui Pertamina Hulu Energi sebagai subholding upstream. Gold sponsors: BP Indonesia, Mubadala Petroleum, Medco Energi, Schlumberger. Silver sponsors: Chevron, ExxonMobil, Inpex, Petronas, Premier Oil, Harbor Energy Company. Bronze sponsor: Repsol, supported by Indonesian Ministry of Energy and Mineral Resources and Special Task Force for Upstream Oil and Gas Business Activities. Organized by Indonesian Petroleum Association and co-organized by Diandra Promosindo.
Ladies and gentlemen, good afternoon. Very warm welcome to the 45th IPA Conventions and Exhibition Technical 2021.
Bu Putri, excuse me, you are still mute. Can you unmute your microphone?
Sorry, thank you, Palio. So my name is Putri Wisman from ConocoPhillips. I'm your session chair for session 1 with my colleague Palio.
Yeah, I'm Leonard Alisapali from Independent.
In this first session about geoscience rock physics, we will have 3 topics to be presented. They are rock physics diagnostic as a prerequisites for petrophysics, regional topsoil analysis in offshore Madura with integrated methods, and analytical method to estimate overpressure magnitude. Next slide, please. Please respect copyright of this event by IPA by not producing, storing, or transcribing in any form without written permission from the IPA. Please do ask clear questions or comment to related topic via question and answer room for participants, and please do not record or screen capture this event. You are all encouraged and expected to be active and participate by asking questions and comment anytime during the presentation. So let's start the first presentations, rock physics diagnostic as a prerequisite for optimal petrophysics by Akas and Hilman Khairi. Akas has a bachelor degree from University of Petroleum and Energy Studies, India, and has a master degree, that's interesting, Master in Innovation and Entrepreneurships from France, and has a few publications. The latest one is Rock Physics Diagnostics for prediction for successful modeling in the EMP magazine, June 2021. And the co-author is Mas Hilvan Khairi from Pertamina Hulu Energy. Without further ado, Akash, floor is yours.
Hello everyone, my name is Akash Mathur and today I'll be presenting my paper titled Rock Physics Diagnostics as a Prerequisite for Optimal Petrophysics. This work has been carried out by me along with Hilfan Khairi from Pertamina Hulu Energy. The abstract for my presentation and paper mainly focuses on the viability of using sonic log for the petrophysical computation, including the porosity. The most widely accepted equations for porosity computation are Wiley time average, Hunt-Reamer-Gardner, and their approximations. Below are the equations for Wiley approximation, and Reamer. In Wiley approximation, we can see that there is also a CP factor, which is the compaction correction factor. From the previous equations, we can see that there are majorly three unknowns. That is the DT matrix or the transit time in matrix, DT fluid or the transit time in fluid, and CP, which is often the compaction correction factor in the unconsolidated formations. Since these equations are empirical in nature, they have their shortcomings, and without proper data analysis, we might end up in iterating the matrix and the fluid endpoints just to fit the petrophysical model to the core porosity or other estimates of porosities. It's important to understand the porosity velocity relationship from the data for successful petrophysical evaluation. We would be going through the step-by-step rock physics diagnostic approach where we'll be checking the viability of using the sonic log for the porosity computation in the petrophysical model. The content for this presentation will be the data overview and the QC. We'll be looking into the data availability and the quality control of the data, followed by the rock physics diagnostic methodology. Next, rock physics diagnostic using the empirical relationships of Wiley time average and Reamer-Gardner, and then rock physics diagnostic using theoretical rock physics model. And finally, we'll put our conclusions in the final slides. This slide discusses about the data availability. We have four wells in here, A, B, C, and D. The lithology is sand shale with calcite streaks and coals in between. The data is from fluvial deltaic environment, and the depth ranges from 200 meter TVDSs to 2600 meter TVDSs. We have the basic log suites available with us that also has the P-sonic and the shear sonic data. The right side shows the log plots with the different available curves for all the four wells A, B, C, and D. This slide talks about the data QC process. We use several crossplots together to identify any spurious data that is present for this formation, or in general, identify the different lithologies. Here is a crossplot of neutron and density. Here we could identify the different calcite streaks, hydrocarbon sands, coals, and in general, the sand shale lithology. The second crossplot is density versus VP, where again, we could identify the different lithologies. Also, we could check the consistency between the wells. Most of the data points here are generally in good condition. The third crossplot is between VP and VS overlain by constant VP by VS lines. In here, we can see that well A in blue color shows an inconsistent trend. For further clarification, we try to do the depth trend analysis using the P-sonic or the VP curve. So in general, VP follows the correct depth trend analysis for all the wells. But the cross plot of VS versus TVDSs shows us that well A in blue colors has an inconsistent VS strength. This confirms analysis that the shear data in well A is spurious and cannot be used directly for seismic reservoir characterization work. But for the purpose of our study, where we are trying to compute the porosity, we just require a reasonable quality P-sonic curve, which is present in here. Here we discuss the rock physics diagnostics methodology. The key steps are as below. First, we prepare a crossplot between density porosity versus velocity, or simply density versus velocity crossplot. The density porosity has been computed using rho matrix as 2.65 and density of water as 1 gram per cc. This is because we are analyzing the data just for the clean formation with volume of clay less than 5% and 100% brine saturated data points. For rock physics diagnostics, we need to bring the data at common lithology and fluid saturations. We then identify different clusters. So from the data here, we can identify two separate clusters, majorly the black cluster and the gray cluster. In terms of depth, the gray cluster refers to data points less than 1500 meter TVDSS, and the black cluster is for data points above 1500 meter TVDSS. Once this crossplot has been prepared, we would start performing the analysis using empirical equations like Wiley time average, Raymer-Hurd-Gardner equation, and then later on the theoretical rock physics model. Here we'll discuss about the rock physics diagnostics using Wiley time average equation. We would want to assess the impact of DT quartz and DT water on the sonic porosity computation. First, we would assess the impact of DT of quartz on the sonic porosity computation. For that, we prepare crossplot of density porosity versus VP. In here, we vary the DT matrix between 55.6 and 115.6. In here, we can see that in order to match the sonic porosity with density porosity, we need to take DT quartz as 115.6. This is very unreasonable. Similarly, for deeper formation, we would need to take a DT quartz between 65 and 75 microsecond per feet. Again, this is very unreasonable. We follow the same process by varying the DT of water. In here, we can see that in order to match the sonic porosity with density porosity, we need to take value of DT water greater than 289 microsecond per feet. Similarly, for deeper formation, in order to match sonic porosity with the density porosity, we need to take DT water between 220 to 230 microsecond per feet. Again, this is unreasonable. So here we can see that in order to get accurate porosity from the sonic, we need to take unreasonable matrix and fluid endpoints. Therefore, this also means that Wiley time average in its original form is not applicable in here. One of the possible reasons for this is that the rock is unconsolidated. If we assume the rock to be unconsolidated, we would want to use the Wiley time average approximation equation, which allows us to use compaction correction factor CP to empirically fit sonic porosity to actual porosity. By definition of the literature, CP is equal to DT in the nearby shales divided by 100. So we would try to compare if the CP that is required to fit the sonic porosity with the density porosity is the same as what we could compute from the DT shale. In here, we can see that from the first cross plot, in order to match sonic porosity with the density porosity, we require a CP value of 1.85 for the shallow formation and 1.3 for the deeper formation or the black formation in here. Although the DT shale by 100 is 1.35 for the shallow section and 1 for the deeper section, this means that the CP required is not equal to the CP calculation from DT shale. This means that a multiplier is required to empirically fit sonic porosity to the density porosity. This multiplier is treated as a fudge factor. So basically, there is no theoretical significance of using a multiplier just to match the sonic porosity with the density porosity. And this kind of multipliers is just an empirically fitting approach with no theoretical significance. In order to better visualize the correlation between the density porosity and sonic porosity, as a first step, we start computing the porosity with dt of quartz as 55.6, dt of water as 189 without any compaction correction factor. We compute the sonic porosity using deterministic approach. In here, we can see in the cross plot that there is a big mismatch between the density porosity and the sonic porosity. Sonic porosity in general has over predicted the porosity in the formations, except for the data points above 2000 meter, which are basically the yellow data points that we could see. It's important to notice the effect of using the sonic log directly in the inverse statistical process, or often referred to as the multi-min process. On the right side image, we can see the results from this approach. The first log plot shows the clean section, brine saturated section, where the p-sonic curve has not been incorporated. The second last track shows the comparison between the density porosity and the porosity computed from the multimin without incorporating the p-sonic log. Here you can see the red curve, which is the phi t underscore mm from the multimin, matches very well with the actual density porosity. The right log plot incorporates the sonic log in the petrophysical model. Once we incorporate the sonic log, the model biases its results towards the sonic data, and therefore you can see that the phi t underscore mm, that is the porosity using the p-sonic curve, actually over predicts for the porosity. For these multi-mineral petrophysics, we have incorporated all the traditional curves like the gamma ray, neutron density for the volume of clay and the volume of quartz and the fluid volumes. In this slide, we are going to check the impact of the compaction factor and try to see if by varying the compaction factor, we can actually fit the sonic porosity with the density porosity. So on the top image, we have the density porosity versus sonic porosity cross plot. The central line is where the sonic porosity and the density porosity are equal. In here, we can see that overall for most of the rock, the sonic porosity has over predicted the porosity except for the depths greater than 2000 meter TVDSs, which is this section, the yellow data points. In the below image, we have the same Wiley time average porosity computed, but now we try to vary the CP so that we can empirically fit the sonic porosity with the density porosity. In here, you can see that there is a reasonable good match between the density porosity and the sonic porosity. However, for data points greater than 2000 meter TVDSs now shows the under prediction of porosity. This means that even though this data is from the same formation, which is from the black formation, a different CP value is required to fit this data to the density porosity or the actual porosity. It's actually impractical to keep on varying the CP factor at few meters just to fit the sonic porosity with the density porosity. When we are dealing with large formations or when we are doing the field-wide petrophysical study, it really is an impractical approach to keep on varying this CP value or using a multiplier just to empirically fit the sonic porosity with the actual porosity. In this slide, we try to perform the rock physics diagnostics using Raymer-Hurd-Gardner equation. As with Wiley equation, we perform the same steps using the Raymer-Hurd-Gardner equation. We make a cross plot of density porosity versus VP, and we overlay it by varying dt quartz lines. So here we have a DT matrix or DT quartz of 55.6, which is the widely accepted value for the DT of quartz. And then we vary it up to 115.6 microsecond per feet. In general, we can observe that a DT matrix of 55.6 does not cover the data points for the gray formation as well as the black formation in here. When we try to incorporate or use or compute the porosity from the Raymer-Hurd-Gardner equation with 50.6 a microsecond per feet as the DT matrix, we can see that we are overestimating the sonic porosity when we try to compare it with the density porosity. So again, as we looked into the previous Wiley approximation, even in here, we can see that the rock looks to be unconsolidated and Raymer-Hurd-Gardner in its original form is not applicable here. So Wiley time average equation is not applicable to this data, as well as Raymer-Hurd-Gardner also is not applicable to this data set. In this slide, we discuss about the rock physics diagnostics using theoretical rock physics model. For this, we prepare a cross plot again of the density, porosity, and velocity and overlay the data with rock physics models. Here we are using two rock physics models, namely the unconsolidated sand model and the contact cement model. The yellow trend is for the cemented model with lower quartz cement percent, and the green trend is for the contact cement model with a higher cement percentage of quartz. When we try to relate it with depth, we can see that for the data below 1500 meter TVDSS falls exactly on the unconsolidated sand model. This means that below 1500 meter TVDSS, the rock is completely unconsolidated. Whereas for the data between 1500 to 2000 meter, the rock is partially cemented. And for the data above 2000 meter TVDSS, the rock has a higher cement percentage. This gives us a reasonable explanation why the Wiley time average equation gave a good match to the density porosity for data points above 2000 meter TVDSS, because the cement has now made the rock well consolidated. But for the depths below 2000 meter TVDSS, even though there is a partial cement present, but still the rock is not well consolidated enough. So using theoretical rock physics diagnostic approach, here we can actually demarcate the different regimes of consolidation, one being the unconsolidated state, the other being the poorly consolidated state, and finally the well consolidated state. Our assumptions from this rock physics model has also been calibrated from the core data in the field. From the petrographic information, we could actually see that the unconsolidated formation does not have any cement percentage. And for the data between 1500 and 2000 meter TVDSS, there is 2 to 3% of quartz cementation. And for the depths greater than 2000 meter TVDSS, there is even a higher cement percentage of quartz. Therefore, our rock physics diagnostic has provided much greater insights than the traditional empirical approaches of Wiley or Raymer-Hurd-Gardner equation. In conclusions, we can say that from the above analysis for this particular data set, that Wiley time average and Raymer-Hurd-Gardner relation in their original form are not applicable to the unconsolidated and the partially cemented formations that we have in here. Again, without assessing the compaction state of the rock, we could end up in iterating the endpoints for matrix and fluids. Compaction factor that are a part of the Wiley time average and the Raymer-Hurd-Gardner approximation are just treated as a fitting parameter. It's really impractical to vary this parameter every few meters as the rock changes its compaction state from unconsolidated to poorly consolidated and then to well consolidated state, as we saw in the previous slide. Theoretical rock physics model provides better insight into the rock's grain scale properties and can help to demarcate the boundary between the unconsolidated to poorly consolidated to well consolidated state. And finally, The overall rock physics diagnostic process is very, very essential and should be treated as a prerequisite before incorporating the sonic data in the petrophysical model. Thank you all. That was the last slide from my side. Thank you.
Thank you, Akash. It's a great presentations and discussions. Thank you for you and for the co-author and also all audience who attending this presentation today. So if you have any questions, so thank you for your attendance to the oral presentation technical sessions 45th IPA Convex. So do you have any questions? We open for the questions. Oh, there is a one. Okay, from Zane. I will read it for you. Is it possible to use theoretical rock physics model, for example, like unconsolidated line or contact cement and etc., for statistical or multi minerals analysis?
Yeah, so basically, this rock physics diagnostic approach using a theoretical rock physics model could be used to identify if the sonic data could be used in the multi-mineral model, because if we, or let's say any deterministic petrophysics as well. The reason is that whenever we are trying to do the multi-mineral modeling, we have to select between the linear and the non-linear model, right? So when we are taking the linear model, we are moving towards the Wiley time average equation, which is the original form. And when we are going for a non-linear form, or let's say a compaction factor is involved, then we are moving towards the non-linearity side. So it's a step to determine if you could use it, but it's not a step to compute the porosity, because it's a relationship between porosity and velocity. So it's one of the first steps to identify if the sonic could be used in the petrophysics or not. So yeah, so generally it's always recommended that we first go for this step, then decide if we should use the sonic or not, because if ultimately like it's the only thing that is available, then it becomes an issue, and then we should be very careful when using sonic. Yeah.
Okay, thank you. Anybody else have a questions? Please type in your Q&A box. We still have 4 minutes to go. Otherwise, I'm just wondering, Akash,
Yeah.
have you tried using another methods like Crieff equations?
Yeah, so basically for this data set, I haven't tried Crieff, and the reason being is that Crieff is not a very popular method in the petrophysics domain. So the study that we do, usually what happens that for all the methods, Wiley, Raymer, Hearn, Gardner, these are some of the very, very popular equations. But even if we go for the Crieff equation, I would assume that since it's also derived from the empirical relation, it would also have certain shortcomings, because again, it's not a theoretical, full-fledged theoretical rock physics model.
Okay, thank you. We have another questions for you. Is from your experience, what do you think? You prefer to choose Wiley time average rather than Raymer, Hahn, Gardner, or the other way around?
Yeah, so for always my preference is usually what I do is I try to avoid sonic, right, until and unless there is an absolute necessity, right? For example, usually what happens is that we would try to prefer, let's say, neutron density combinations for the porosity computation, right? So sonic is something I generally avoid, because in most of the scenarios I have seen that it's not applicable in there. So, and again, if let's say if I have to use, then if there is no other choice, then I would prefer to first go for rock physics diagnostic and see which one gives me better, whether the Wiley time average equation or Raymer, Hearn, Gardner. So it's no absolute kind of rule that we should always use that.
Okay, thank you. I guess this is gonna be last questions.
There's another one. Sorry.
Oh, Pak Leo already have it. There is another questions. You know how to select which rock physics model. I guess I mean in this case, did you do any modifications of the parameters, for example? So this is from Zain.
Yeah. So basically, the first step for any rock physics diagnostic is to bring all the data points to a common lithology and the fluid scenario, right? So what we need to do is we need to discriminate first the clean section, right? So when, let's say in here, you will see that I've taken a very, very clean section. Volume of clay is less than 5%, right? So that means the only thing that is applicable is the quartz section, right? So majority of the data points will be pure quartz. So now when we are doing the rock physics diagnostics, what we do is we simply put the data points on the cross plot and overlay it by the theoretical rock physics model. So whatever theoretical rock physics model say, that is your model. So for example, in this case, I have not tried to change any of the parameters. By default, this rock physics model will justify your data and will give you an indication that this is an unconsolidated model or whether this is a consolidated model, cemented model, right? So just we need to be careful that we are looking at the common lithology and common fluid scenario. So first, if you are looking at the brine saturated, take all the data points which are brine saturated, or if you're taking hydrocarbon saturated, take all the data points at a common hydrocarbon saturation, and the model itself will fall on your data set automatically and give you the answer.
Okay, thank you so much. I guess we are running out of time, Pak Leo. Perhaps, yeah, you may want to send Aka's email. So this is a great discussion, great presentation. So if you want to know about this paper, you can download it at the IPA website. And next slide, please. There is supposed to be Aka's email. Okay, Aka's email is akash.matur@cgg.com. I will type it in the chat box, so for everybody to contact Akash later on. Thank you so much. So we're gonna have another topics, which is regional top seal capacity analysis in GS1 Ridge offshore Madura involving seal geometry, capillary seal, hydrofracturing analysis, and natural fractures modeling. Next slide, please. The main author is Gaddafi, has a bachelor in geology from Pajajaran University, and as well having a master in geology from ITB. So he has a few previous publications. The latest one is New Play Transitional Classic Reservoir in Bidal Miocene in the JCY 2019. She's working for a PHE WMO in Jakarta. And the co-author is Pak Agus, Rizky, Pak Andre, and Mas Gufron. Without further ado, floor is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone, and thank you to the chairman for the time given to us to present our paper. I will present a paper with the title Regional Top Seal Capacity Analysis in JS1 Ridge, Offshore Madura involving seal geometry, capillary seal, hydrofracturing analysis, and the natural fracture modeling. The content of the presentation will include a 5 sections consisting of the background of the topic, regional geology of the research area, data and method used for the analysis, the result of the analysis and discussion, and the last is conclusion. The study area is prolific oil and gas field producing in the offshore Northeast Java Basin, which is produced from the early Miocene reef built-up Kujung 1 formation. As we can see it on the well section A to B, there are varying height of the hydrocarbon column in the Kujung 1 reservoir that affect the exploration success rate in this area. The regional seal of the Kujung 1 reservoir is the mid-Miocene shale of Rancak, and the seal is believed taken role with the varying height column of hydrocarbon in Kujung 1 reservoir. The study to have the understanding the character and the capacity of the Rancak as the seal rock of the Kujung formation. Early Miocene Kujung 1 carbonate formation deposited on a JS1 reef basement high with a northeast-southwest trending. It consists coral reef that developed in the back reef lagoon environment during early Miocene translation and then drowning in the middle Miocene. In the top of it was deposited shale with intercalcent sandstone and the limestone of the shallow marine sediment of the middle Miocene Rancak unit. There are two structural trends developed in this area. The first is a series northeast-southwest trending of the horse graben structure that control the initial configuration of the basin formation during Paleogene. The second is the middle Miocene to the Pleo-Pleistocene tectonic, which reactivated the existing structure and formed east-west directed structure. The analysis using 41 wells consisted of exploration and development wells. Only 3 wells with the complete data to be used for pore pressure, capillary seal, and the fracture model analysis. In general, hydrocarbon leakage is caused by capillary seal failure, seal geometry failure, and or seal integrity failure. The capillary seal failure when the hydrocarbon buoyancy pressure more than the capillary entry pressure of the seal rock, it will cause hydrocarbon to migrate vertically. Seal geometry related to the structural position, thickness, coverage area of the sea rock to the reservoir or structure. Even if thickness of the sea rock does not influence to the capillary entry pressure, but is critical to integrity of seal to fracture. Hydrofracturing failure if the hydrocarbon buoyancy greater than the fracture gradient pressure. And fracture and fold will provide high permeability pathway for the hydrocarbon to escape from the trap or structure. Here's the workflow of the study. The first step of the study is literature study and then data collection. The MICP data from the lab analysis is used to calculate capillary entry pressure in the hydrocarbon water system. And then next is used to estimate maximum column hydrocarbon can hold by capillaries of shale. MATLAB, core, and isopa map is used to generate sand, shale, and carbonate ratio, shale thickness, and facies distribution for shale geometry analysis. An actual column hydrocarbon is used for reality check for the all analysis. Drilling report featuring a reflectant, XRD, and well log is used to generate pressure profile and hydrofracturing seal analysis. Before we generate fracture modeling, we should calculate elastic property and rock strain and estimate drilling-induced fracture to know orientation of stress and estimate the magnitude of the stress. These 4 elements analyzed to construct understanding the regional topsoil in the study area. Now we are moved to the pore pressure analysis. This analysis conducted in the 3 wells. Let's focus on the KD3 well as the deeper well. The pore pressure estimation based on the Eaton method shows slight overpressure in the unit Rancak. This slight overpressure is also reflected in the increase of drilling mud weight. The Rancak unit sedimentation rate around 240 to 400 meters per million years, and with rate sedimentation greater than 100 meters per million years can cause loading mechanism overpressure referred to swarbreak. For the unloading mechanism, as the hydrocarbon generation and the smectite to illite transformation, it occur in the deeper formation. It shows from the KD1, KD2, and the KD3 wells. The vitrinate reflectance value below the Rancak unit greater than 0.6% RO as indication source rock starting to mature. And in the KD3 wells, temperature greater than 80 degrees Celsius reach at the depth 1,500 meter, which is below the Rancak unit. It corresponds with the density sonic clock crossplot, which indicate the conversion of the smectite to illite. And it is consistent with the clay mineral diffraction data XRD at the 3 depth in the KD3 wells. This is well section and pressure profile from the south to the north from the KD3, KD2 and KD1 wells. And unit Rancak show a slight overpressure. It's considered overpressure within unit Rancak is driven by loading mechanism, while deeper formation driven by unloading mechanism. Next is hydrofracturing analysis. This analysis using 41 well data. The hydrofracturing shell is the pressure window between the fracture gradient to the aquifer pressure. The fracture gradient determined using the Matthew and Kelly method. The result of a hydrofracturing analysis is the Rancak unit has a hydrofracturing shell capacity to hold the gas column buoyancy with a range from the 700 to 1,500 meters. The hydrostatic aquifer pressure in the Kujung 1 reservoir resulted in the wide window of the hydrofracturing shell capacity and a thick hydrocarbon column capacity. In other words, the shell capacity exceeds the maximum closure height and the reservoir thickness. It means there are no issue with the hydrofracturing shell to hold hydrocarbon in Kujung 1 reservoir. Okay, next. The hydrofracturing is not a factor that determines the sealing capacity in the study area, because the aquifer pressure in the Kujung 1 reservoir is hydrostatic. This will be different if we have a hard overpressure aquifer pressure in the HPHT field. The hydrocarbon gradient will reach the fracture gradient of the seal rock and cause leakage as seen on the Genesis and Popeye mini basin in the Gulf of Mexico. Capillary shell analysis. The KD1 well is the only well that has capillary entry pressure test data on the cell of the Rancak unit. The capillary entry pressure is 7.4 megapascal in the mercury air system. To calculate the maximum hydrocarbon column, the conversion of mercury air pressure to hydrocarbon water pressure is needed and can be determined using the following equation. The gas capillary entry pressure is the 1 megapascal, which is equivalent to 114 meter height of the gas column. In reality, the KD1 well has 213 meter gas column height and the 9 meter of the oil, which equivalent to 1.9 megapascal. This difference shows that the gas column buoyancy pressure that can be held by the Rancak unit capillary pressure is smaller than the actual hydrocarbon buoyancy pressure in KD1 well. The presence of the slight overpressure of the 0.95 megapascal at the bottom of the Rancak unit has a role to increasing the Rancak unit seal capacity, which gives it ability to hold the Kujung 1 reservoir gas column up to 221 meters, or equivalent to a pressure of 1.95 megapascal. If we compare with the actual hydrocarbon buoyancy pressure in the 41 wells, with the maximum 1.95 megapascal seal capacity, there will be no issue with the capacity seal of the Rancak unit shell. The Rancak unit is dominated by shale with intercalation limestone in the south part and the sandstone intercalation in the north. This facies change indicated deposition environment from the inner middle shelf in the north into outer shelf in the south. The Rancak unit show fundamental change from the extensive early Miocene Kujung 1 carbonate cycle to the siliciclastic deposition in the middle Miocene. In general, the Rancak unit deposition environment can be divided into the three types. They are the inner middle shelf, outer shelf Bay Reef Lagoon, and outer shelf Sensol Bar. Based on the actual hydrocarbon column in the KD1 well, inner middle shelf of the Ranchak can hold gas column to 230 meters. This concludes the Ranchak facies in inner middle shelf has a good capability as seal rock. We can assume deposition environment in the outer shelf, lagoon, and sand bar have a better good capability as a seal because more thicker and clay rich. Main data needed for the fracture modeling are direction of stress, magnitude of stress, and rock elastic properties. Stress orientation can be identified from the drilling-induced fracture such as breakout or tensile from the image log data. In KD3 well, there are 21 induced tensile fracture in the direction north 7 degree east fracture plane and 126 breakout fracture in the direction of the north 97 degree east. The KD1 well, the log image data is limited in the Kujung-1 interval and no indication of the breakout or induced tensile. However, based on the caliper data, it shows hole enlargement direction at the several depths with the same direction as the KD3 well. Based on the drilling-induced fracture analysis, the maximum horizontal stress is relatively northeast-southwest. Let's move on to rock strain, elastic properties, and in situ stress. Rock strains determine the integrity of the seal rock in responding to subsurface stress. Rock strains modeling involve the correlation between unconfined compressive strain and lock, which are sensitive to the variation in the rock strain, especially sonic lock. And in this study, rock strain was estimated using some empirical equation from a sonic lock. The elastic property of the rock-Young modulus and the Poisson ratio are required for modeling fracture using geomechanical approach. Empirical equation using a sonic dipole measurement can be used to determine the dynamic elastic modulus of rock and also to determine their static elastic modulus. In situ stress of the geomechanical model is used to determine the slip tendency of the fracture to the current stress condition. The geomechanical model was calibrated with the actual breakout from the image log and caliper log to have the reliable data. The resulting geomechanical model show that the stress regime in the KD1 and KD3 wells is a normal regime. SV is greater than SA max is greater than SA min. Natural fracture modeling in the study was carried out in the KD1 area. This is because this area has a closed structural Kujung-1 reef reservoir so that the hydrocarbon supply and migration factor can be ignored. This modeling used to the bottom part of the Ranchak depth structure map, which is sealed the top of the Kujung-1 reef reservoir. The fracture modeling results show the distribution of the fracture around the KD1 area related to the percentage of the hydrocarbon content in the Kujung-1 reservoir. Based on the slip tendency, the fracture have not yet reached the filer envelope under the current stress condition. It can be said that the fracture in the reset area is in a stable or the sealing condition at this time. Okay, next, the percentage of the hydrocarbon content in the Kujung-1 reservoir, which is dominantly less than 100%. The high gas reading in the sandstone interval of the Ranchak unit above the Kujung-1 reservoir in the KD1 field indicate that there has been a hydrocarbon leak from the Kujung-1 reservoir as a tip zone. It is estimated that East Java Basin during the Neogen tectonic period, with the peak in the Pleistocene, the fracture in the study area was in the critical condition and the leak occurrence in the Kujung-1 reservoir. Here some conclusion. The rancak unit pore pressure indicates slight overpressure caused by loading mechanism, while the deeper formation corresponds to the unloading mechanism. The presence of the slight overpressure in the rancak unit has a role to increase the capacity of rancak unit as seal rock. Slight overpressure caused the rancak unit to able to hold gas column up to 221 meters or equal to a pressure of 1.95 megapascal. The rancak unit has the hydrofracturing seal capacity to withstand the buoyancy of the gas column by 780 meters to 1,570 meters. The hydrofracturing capacity of the seal exceeds the maximum closure height and the thickness of the Kujung 1 reservoir in the study area. Seal geometry of the rancak has capability to hold hydrocarbon from the good to excellent. Natural fracture modeling show that the fracture distribution corresponds to the percentage of hydrocarbon filling in the Kujung 1 reservoir. However, based on the slip tendency analysis, the fractures are in the stable condition under current stress condition. Okay, that's all I have. And thank you very much for your kind attention. And thank you to everyone who has supported this paper to be presented in IPA, especially Pak Sugiri and Pertamina EP Cepu Management. Thank you.
Thank you, Mas Kadafi, and all co-authors. It's very interesting study, actually, very comprehensive. Now we are open for the questions and answer. If you have any question, please type in your Q&A room. Thank you. So first questions coming. So basically, is this critical condition will also affect the fault seal capacity if there is any fault?
Okay, thank you for the question, Ibu Najla. The critical condition is also effect to the fault, to the fault, not also and not only on the fracture, but there's effect to the fault. But in this area, we just only have one fault in the west. That's because we are in the juxtaposed to the shell, juxtaposed to the shell. So so the could be the leakage is minimum, okay. But in the study we just only the study of the for the top seal capacity, not lateral seal capacity. That's my question. But for your question, does critical condition will be affect to the fault seal? That's the answer is yes. That's my answer. Thank you.
Thank you. Is there further questions to Mas Kadafi?
Maybe one question from myself, Bu Putri. If I remember in your slide number 10, you include seismic data in your study. Can you explain what did you do with your seismic data, whether you did some seismic inversion or you just use the seismic as it is? Thank you.
Okay, thank you, Pak Leonard. The seismic data is we are used for interpreted the fault polygon and then horizon of the bottom of the rancak formation. Because if you want to generate the fracture modeling, so we have input the Poisson ratio, young modulus, cohesive internal flexion angle, fault polygon, and depth structure. And At this case, the seismic is used for determine the fault polygon and structure map. That's my answer.
Okay, but is there any attempt to calculate the pressure from the seismic data?
Sorry, can you repeat?
Is there any attempt to determine the pressure from the seismic data?
Determine pressure?
Yeah.
No, but the pressure is determined using geomechanical model. Yeah, not from the seismic.
Yeah.
Yes, sir.
Okay, but yeah.
Okay, thank you, Pak Leo. There are more questions coming. Okay, so this is from Pak Tony Celestio. What is or are the quantitative parameters to define the seal geometry when a seal defined as a bad seal geometry, for example?
Okay, thank you, Pak Tony. For the seal geometry, we have 3 parameters to define the character of the seal. First, there is thickness, and then coverage area, and then the facies. The first, the thickness, there is a qualitative interpretation. Yeah, if we have thicker shell, thicker seal that in the top of the reservoir, that will be more better if we compare to the seal. There's only a few meter of thickness. Yeah, and then if we for the coverage area, sometimes we have to know about the distribution of a seal. There's coverage the all of the structure, or just only half of structure. So if they are covers the all structure, all as reservoir, so the quality of the seal geometry is good. Yeah, but if just only there some place they are not covered by a seal, that will be leaking at the time. And for the facies, so we have to define which one is facies is more better to be seal. If we have sandy facies, there's if we compare to the shelly facies, the shelly facies will be more better if we compare to the facies. So that's the parameter when we define which one is seal geometry that have a good or a bad seal. Thank you, Pak.
Thank you. There is another one. Could you clarify if your study linked to Kujung 1 charging with reservoir fracture density or rancak fracture density? I can't hear your voice. You are mute. Okay. Thank you.
Because we run the fracture modeling in the bottom of the rancak, and we are using the elastic property from the interval of the rancak, and then also the rock strength in the rancak interval. The fracture developed there is in the bottom of the seal. There is a rancak formation. Thus, the fracture is above of the Kujung 1 reservoir. Okay, that is my answer.
Thank you. Another questions coming from Ahmad Reza. This study affect the overall strategy of exploitation or production strategy around the area? How is it?
This study is just finished. We not yet using the study for the next well, but we are still working for that for the next prospect. So I hopefully this study can answer the question about the why we have hydrocarbon filling in the closed area is a different. So from this study we have understanding that the fracture is control the hydrocarbon occurrence in every structure in the Kujung Reef. Okay.
Thank you. There's another good questions actually. We only have 1 minute, so only one questions. The Poisson ratio is that you get, which is 0.42, seems to represent a relative soft rocks. Do you have any explanation for that from Pak Ignatius?
Okay, Pak. This we have from the empirical equation, Pak Ignatius. Because we don't have the measurement from the lab analysis for the Poisson ratio in the Rancak, but that we have from the equation, empirical equation, and we are calculate that the value in the Rancak in 3 well, and that's consistent with with another well.
Okay, thank you so much, Mas Kadafi. I'm so sorry we are running out of time. So there are many questions actually. So maybe if you would like to get to know more, you can send email to Mas Kadafi. I'm gonna post his email on this chat box. Thank you so much again for Mas Kadafi and the co-authors. It's great presentations. I over to you, Pak Leo.
Okay, thank you, Bu Putri. I will moderate the last presentation. The last presentation will be delivered by Pak Agus Ramdan from ITB, and the title of his talk will be "The Analytical Method to accurately estimate overpressure magnitude." The case study from Indonesia Tertiary Basins. Next slide, please. So Pak Agus Ramdan is a lecturer from ITB. He got PhD from Durham University in England. He has published some publication, and the last one was done in 2018. There are 2 subjects, and he has also some awards and recognition from his professional career. Next slide. The co-authors of this article is Pak Lambok Hutasoid, lecturer from ITB, and also Pak Arifin from ITB as well. So we give the time for you, Pak Agus, to present your work.
Good afternoon, everyone. In this occasion, I would like to discuss an analytical method to estimate overpressure with the well data from the Lower Kutai and East Java Basins. My name is Agus Ramdan, and I'm a lecturer at the Department of Geology and Department of Groundwater Engineering, Institut Teknologi Bandung in Bandung, West Java, Indonesia. This is the outline of our discussion. First, I'm going to give a brief introductory about previous overpressure study in the Lower Kutai Basin, a very fascinating basin for overpressure study. And secondly, I'm going to discuss a bit theoretical overview on how to analyze the presence of loading and unloading overpressuring from wireline log. Then I'm going to discuss the application of the theoretical background into our dataset from the Lower Kutai Basin, the new interpretation for sure, and into a well from the East Java Basin. Some interesting points are given in the last part of my presentation in discussion and conclusions. I would start my presentation from Lower Kutai well again. This is an extraordinary well penetrating hard overpressure zone as indicated from this RFT data. The RFT data also indicate that top of overpressure is located at the depth around 10,500 feet. And these are density and sonic logs in shale section in this well. And what is interesting is that the response of sonic log to overpressure is more or less the same as indicated by the RFT data at the depth around 10,500 feet, while density log does not respond the overpressure until the depth of 12,000 feet. And the red lines here are moving average of the data with the window of 200 feet. I actually have written some papers to discuss that circumstance in good journals, even resulted in some best paper. However, as always, science doesn't care the best whatsoever. I have some good challenges to my previous interpretations, and here I want to share my newest thought. Hopefully it will last for a while. Otherwise, I will have to write some papers again. And it can also be seen here that for me, it takes around 14 years to understand what is going on in the Lower Kutai Basins in relation with overpressuring. If I summarize our thoughts about the dataset above, then it can probably be divided into this. Pre-2018, we interpreted that the cause of overpressure in the Lower Kutai Basin is solely unloading mechanism without any contribution from loading mechanism. But we have evolved since 2018. We thought that loading also contributes to overpressure in that basin. Now we try to quantify the previously qualitative analysis to make our science more predictive. And yes, ladies and gentlemen, the problem is the same, but I promise you that the answer will be different this time. And as I said, I hope that the answer will last for a while, so I can take some good break. Now I'm going to discuss the signature of overpressure if it is being generated by loading, unloading, or combination of both from wireline logs. To start, overpressure generating mechanism could be grouped into two, loading mechanism and unloading mechanism. Loading mechanism is caused by the increase in one or more principal stresses without accompanied by sufficient water flow from the sedimentary rock system. The principal stress could be vertical caused by rapid sedimentation or lateral stress caused by active tectonic. As a result, rock will fail to compact, and it is commonly termed as disequilibrium compaction or compaction disequilibrium. And pore pressure will elevate in response to the increase in stress. The major overpressure generating mechanism is unloading. Through this process, pore pressure will elevate into overpressure if there is increase in pore fluid or load transfer from load-bearing materials into pore fluid or combination of both. The main geological mechanisms that are responsible for this unloading process are clay diagenesis, for example, smectite to illite transformations, and hydrocarbon generation through transformation from kerogen into hydrocarbon, which producing fluids, as well as transferring load-bearing materials into pore fluid. Now I'm going to discuss the basic pore types, which serve as basic assumption in interpreting wireline log response to different overpressure generations. Bowers and Katsubi in 2002 stated that there are two types of pore in shale, storage pore and connecting pore. The biggest contributor to the total porosity is storage pore, while the biggest contributor in transporting several materials, such as acoustic and electric, is connecting pore. And in wireline log, the bulk porosity, thus the storage pore, is measured by density and neutron logs. For these reasons, density and neutron log are often termed by petrophysicists as bulk properties logs. Meanwhile, flow properties, thus connecting pore, are measured by sonic and resistivity logs. Also, for this reason, petrophysicists often term sonic and resistivity logs as transport properties log. In this presentation, we will use density log representing storage pore and sonic log representing connecting pore. And mechanically, storage pore is relatively rigid, while connecting pore is more flexible due to its aspect ratio. If unloading takes place, for example, by the increase in pore fluid, or commonly termed as fluid expansion, because the connecting pore is flexible, it will open the connecting pore, but it will give negligible impact to storage pore. Therefore, based on the assumption of storage and connecting pores as discussed here, if we have overpressure generated by loading mechanism, then it will only affect bulk porosity or storage pore. It will then be read by density log. And since there is no impact of loading to connecting pore, therefore the sonic log will also reflect bulk properties of the shale. As a consequence, if overpressure is generated by loading mechanism, then overpressure will be responded by both density and sonic logs. If overpressure is caused by unloading mechanism, as mentioned before, it will open the connecting pore and it will be read by sonic log, not by density log. Therefore, if we have overpressure generated by unloading mechanism, then it will only be responded by sonic log, not by density log. And this is a cartoon to illustrate wireline log responses for different overpressure mechanism. Loading overpressuring will be responded by the density and sonic logs, while unloading overpressuring will only be responded by sonic log, not by density log. It can also be inferred from the circumstance that density log is unique indicator for overpressure that is being generated by loading mechanism. Now, how if both loading and unloading are the generating mechanism of overpressure? Dutta in 2001 stated that density and sonic log response are proportionally linear for overpressure that is generated only by loading mechanism. If sonic log response is stronger than the response of density log, then it can be deducted that unloading contributes to overpressure in a given well. This linear proportionality also makes us unable to construct the expected sonic response to loading, thus loading contribution to total overpressure by using density log. Okay, that's the theory, and now I'm going to test the theory to the dataset from the Lower Kutai Basin and East Java Basin. We are back again to this extraordinary well. As discussed earlier, repeat formation tester indicates that top of overpressure is located at the depth of 10,500 feet and this top of overpressure is responded by sonic log. Density log does not give response to overpressure until the depth of 12,000 feet. It can be inferred from the circumstance that the first appearance of overpressure is caused by unloading mechanism, and loading starts to contribute to overpressure at the depth 12,000 feet. And this is our new interpretation to overpressure in this well. And as mentioned in theoretical background, it is possible to construct sonic response to loading from density log, since density log is unique for loading mechanism. Also, as mentioned, the relation between sonic and density is linear in loading section. Here, we are certain that down to the depth of 10,500 feet in hydrostatic zone, there is no unloading effect. We can then establish linear relation in this section and then extrapolate the equation into section below to obtain sonic response to loading. By applying these techniques, the result in sonic response to loading is shown in this green color. After discriminating sonic response to loading, we are able to calculate the contribution of loading to total overpressure by applying analytical methods such as Bauer's method for loading or equivalent depth method. In this well, we use Bauer's method for loading. And this is the equation relating vertical stress and velocity, or reciprocal of sonic. And the green line is the resulting pore pressure contribution due to loading in this well. Loading start to contribute to overpressure at 12,000 feet down to the TD of this well. After we calculate contribution of loading to overpressure, the last step is to calculate total overpressure due to loading and unloading. We also apply Bauer's equation for unloading, and here is the relation between vertical stress and velocity for unloading. And this calculation requires the effective stress history of the sediment, which is equal to effective stress due to loading as obtained from previous step, and also velocity response to loading, also obtained from previous step. Subscript L here is used to give the index of those loading influence to total overpressure. This equation also requires unloading parameter U, and we found that U equals to 4 is sufficient to estimate overpressure in this well. This U value is considered high, implying that the shale in the study area is more plastic. Okay, that's the dataset from the Lower Kutai, and now I'm going to apply the same methodology into dataset from the East Java Basin. This is also an extraordinary well in terms of overpressure. It can be seen from reversals in density and sonic log that overpressure starts to appear very shallow at the depth of 1,000 feet, and geologic information reveals that erosion in this well is negligible, and therefore it can be said that a top of overpressure is considered at its maximum burial depth. The top of overpressure in this well, 1,000 feet, is considered very shallow, and probably, to my knowledge, this is one of the shallowest top of overpressure in Indonesia. Overpressure in this well is responded by density and sonic log, and also down to the TD of this well, 3,000 feet, temperature has not sufficient yet to generate any plausible unloading mechanism, such as clay diagenesis and hydrocarbon maturation. It then can be interpreted that loading is the only cause of overpressure in this well. Here, I want to demonstrate the use of simple equivalent depth method to estimate overpressure that is being generated only by loading mechanism. The equivalent depth method is actually the same as Bauer's method for loading, stating that for the rock having the same porosity or velocity or transit time in this case, will have the same effective stress. For examples, the effective stress at point A here, which is overpressure, equals to effective stress at point B here, which is hydrostatic. For these reasons, equivalent depth method is commonly termed as a vertical method. This is just to refresh that according to Terzaghi, the effective stress is obtained by subtracting pore pressure from overburden, or graphically, it is the distance between overburden and pore pressure as indicated by this double arrow line. For hydrostatic pore pressure, effective stress will increase with increasing depth. Applying the equivalent depth principle into the East Java Basin dataset results in this condition. The effective stress at overpressure section, for example at the depth 1500, 2000, 2500 feet, equals to effective stress at the depth of 900 feet. And as mentioned before, we are able to calculate graphically the value of effective stress at the depth of 900 feet, since the pore pressure is hydrostatic. And this is the effective stress at the depth of 900 feet, which is the distance between pore pressure and vertical stress. And the effective stress at the depth of 900 feet is similar to effective stress at 1500 feet. And also similar to effective stress at 1500 feet. And therefore, this is the resulting shale pore pressure in this well. It can be seen that simple equivalent depth method works very well in this well. I think it should be work since the only generating mechanism in this well is only loading. And as always, the theory is always superior. Okay, now I'm going to give some interesting points in discussion. First, this paper has demonstrated that to be able to accurately estimate overpressure magnitude, we need to know the generating mechanism of overpressure. I think our science is quite similar to the field of medicine. Medical doctors need to know the cause before they give some recipes. And this research also reveals new interpretation of overpressuring in the lower Kutai Basin. It is very unique. Loading and unloading contribute to overpressure in this well, but unloading starts to contribute at shallower depth compared to contribution of unloading to total overpressure. And for this Java Basin dataset, this analysis reveals that loading is the only cause of overpressure in that well. And just to conclude from my work, we have developed more robust workflow for overpressure estimation. First, before the workflow, in analyzing overpressure generating mechanism and also in estimating the magnitude of overpressure, the density log is compulsory. Without density log, it is not possible to calculate each contribution of mechanism to total overpressure. And second, we need to choose appropriate method to estimate overpressure based on its generating mechanism by applying analytical method such as Bauer's method both for loading and unloading. And also we have demonstrated that the resulted workflow has given satisfactory results in analyzing and estimating overpressure in Lower Kutai and East Java. We also have tested the method for the wells in the North Sumatra, South Sumatra, and Tarakan, and it also gives satisfactory results. And lastly, the understanding of generating mechanism of overpressure is important not only for estimating overpressure magnitude, but also to analyze the relationship between overpressure and petroleum system that is usually performed during a basin modeling. Thank you very much for listening. And if you have some question, we can have a discussion.
Okay, thank you very much for your presentation, Pak Agus. Nice presentation. We have some question here. First, we have one from Pak Riki. What is the importance of knowing the overpressure mechanism, loading or unloading in drilling? That's the first question. Maybe you can answer it directly, Pak.
Yeah, thank you very much, Pak Riki. It's a very good question. Thank you for asking these important questions. So the understanding of generating a mechanism of overpressure is very important in determining the method that we will use to estimate overpressure magnitude. So without understanding the generating mechanism, I think it is not possible to accurately estimate overpressure because certain method only works for a certain generating mechanism, things like that. For example, if we want to apply equivalent depth method, it only apply to overpressure that is being generated by loading mechanism or disequilibrium compaction. That's my answer, Pak.
Okay, Pak. The next question is it common to have the unloading first, then loading?
I think this is the special
Please
case.
enlighten, Pak.
Yeah, I think this is the special case from the Lower Kutai Basin, Pak. So I have analyzed overpressure in several basins in western part of Indonesia. Loading usually comes first, and then at depth, unloading start to contribute to overpressure. But this Kutai Basin is very special. It's a very particular place on Earth, I can say, because we have unloading first, and then at depth, loading start to contribute to overpressure. So it's a very fascinating data set from the Lower Kutai Basin. Thank you, Pak.
Okay, Pak. Thank you. The next question is coming from Pak Agung. If there are anomalies are responded both by sonic and density logs,
Okay.
it means that the generating mechanism will be both loading and unloading, or can it be only one generating mechanism?
Okay, thank you very much, Pak Agung. This is also a very good question. So if we have overpressure that is responded by density log and sonic log, and the response between density and sonic is linearly comparable, then we can interpret that the cause of overpressure is only loading mechanism. But if the overpressure still being responded by sonic and density log, but the response of density log is stronger than the response of density log, or out of the linearity, then we can interpret that the cause of overpressure is combination between loading and unloading mechanism. And that is the case in the Lower Kutai Basin, starting at the depth of around 12,000 feet, in my case, down to the TD of this well around 14,000 to 15,000 feet. So that's my answer. Thank you very much.
Okay, Pak. The next question coming from Pak Minarwan. Does the unloading, for example, by HH generation, actually preserve pore space or open up the space?
Oh, okay, thank you very much, Pak Minarwan, for the questions. So based on the theory of connecting pore and storage pore, and due to its aspect ratio, if we have fluid coming to the shale system, then it will open only the connecting pore So that's the poroelastic response, because the connecting pore has a very high aspect ratio, so it's more flexible compared to the storage pore. So if we have unloading mechanism, for example, hydrocarbon generation or transformation from smectite to illite that are producing some water, then the waters will be accommodated by the opening of only the connecting pore, not the storage pore. And in the case of overpressuring, that's why if we have overpressure being generated by unloading mechanism, then it will be responded by sonic log because of the opening of the connecting pore. Thank you very much, Pak Leo.
Okay, Pak. The one more question from Pak Zain. Do you consider the exponential equation for transit time versus density for this equilibrium compaction analog to Gardner empirical equation, which is exponential?
Yeah. So if we try to make a relation between density and sonic law, then we will have two lines. In this case, Duta in 2002 has made some research that the first line equals to smectitic line and the second line equals to the elliptic line, the deeper one. If we compare that line with the Gardner equation, then probably the Gardner, of course, Gardner relates velocity as a reciprocal of sonic with density. The smectitic line equals to the lower bound of the Gardner equations, and the elliptic line equals to the upper bound of the Gardner's equations. So it's quite similar with the Gardner, but at that time Gardner didn't give any explanation what's the meaning of the lower bound and what's the meaning of the upper bound. And Duta in 2002 gives some meaning that the lower bound equals to the smectitic line and the upper bound equals to the elliptic line. So that's my answer, Pak Leo. A very important question. Thank you very much.
Okay, but thank you very much. We still have some question, but unfortunately we need to stop as scheduled. So we thank you, Pak, for your very nice presentation. We give a big applause for you.
Terima kasih.
Okay, thanks all for coming to this session. Hope you enjoyed all presentation. And we still have some session that you can visit and learn about what people have done. So we thank everybody, especially for the presenters. Thank you very much. And we want to just remind you that this event can happen by help from some sponsors. So I think the committee can show us the sponsor slide.
Platinum sponsor Pertamina melalui Pertamina Hulu Energi sebagai subholding upstream. Gold sponsors BP Indonesia, Mubadala Petroleum, Medco Energi, Schlumberger. Silver sponsors Chevron, ExxonMobil, Inpex, Petronas, Premier Oil, Harbor Energy Company. Bronze sponsor Repsol, supported by Indonesian Ministry of Energy and Mineral Resources and Special Task Force for Upstream Oil and Gas Business Activities. Organized by Indonesian Petroleum Association. Platinum sponsor, Pertamina, melalui Pertamina Hulu Energi sebagai subholding upstream. Gold sponsors, BP Indonesia, Mubadala Petroleum, Medco Energi, Schlumberger. Silver sponsors, Chevron, ExxonMobil, Inpex, Petronas, Premier Oil, A Harbor Energy Company. Bronze sponsor, Repsol, supported by Indonesian Ministry of Energy and Mineral Resources and Special Task Force for Upstream Oil and Gas Business Activities. Organized by Indonesian Petroleum Association and co-organized by Diandra Promosindo.